Michael and I will manage, I guess, this presentation is I will go through, I guess, the main bulk of the information. And Michael is one of my PhD supervisors, and this is really a lot of the work that he's advised me on and has been an absolute crux in getting this to happen. So Michael will be able to explain everything regarding multi-state modeling a lot better than I will, and has been instrumental, as I mentioned, in actually doing this kind of methodologies in the context of tuberculosis. So whilst I will run through the main portion of the slides, Michael will chime in and provide more detail about multi-state modeling, and I'm sure also will answer a lot of your questions as well. So this is something that was recently published in the Lancet Global Health a couple months ago now, and we presented this at the Union last year. So I think I see some familiar faces on this call. I did have some individual conversations about this. So whilst we will go over the results of this study, a lot of this will actually focus on the application of multi-state modeling as well and the future in tuberculosis. So I think I'm preaching to the choir when I say that the binary characterization of tuberculosis obscures a spectrum. So the dots era binary model of latent tuberculosis versus active tuberculosis actually is not really that binary. It's not that simple. The modern spectrum conceptualization actually shows that you go from non-detectable or no immunological activity to dysregulated. You have variability in chest X-ray pathology and bacterial burden and also in symptoms. And every person can vary in different levels between those different categories. And so actually sticking with this dots era binary model obscures and oversimplifies this dynamic infection and disease states and really limits risk stratification efforts, as we've seen through multitudes of studies. And so what we did for the studies, we took a framework that was proposed a few years ago now, the ISTB framework, or the International Consensus on Early TB framework, where the authors kind of broke down the spectrum into different categories, which was split based on what I mentioned before of pathology. So that's chest X-ray, etc., infectiousness defined by bacterial burden, and then symptoms and signs, which is a way to, I guess, categorize the spectrum a bit more detailed than just active and binary. And so what we did is we decided to try and apply this conceptual framework into the Erase TB study. And there are some limitations into how we actually could apply this framework in practice, which I will discuss later. But in brief, we have people with no MTB infection in the study who are not pictured here in this framework. And we have MTB infection, so it's an absence of all three of those categories. And then we move from asymptomatic TB non-infectious. And I will note that the framework is initially published as subclinical and clinical, but we have changed the wording to asymptomatic and symptomatic in this analysis. And then from non-infectious to infectious tuberculosis. And I'll provide a bit more information about Erase TB. So Erase TB was a large longitudinal observational cohort study where we recruited 2,100 household contacts of people with tuberculosis. And these people with TB were defined as highly infectious. So their gene expert result was medium or high. And we recruited 700 people per country. So 3 countries were enrolled where we recruited, so Zimbabwe, Mozambique, and Tanzania. Every household contact was followed up on a 6-monthly basis for a period up to 24 months. And at every visit, they underwent anthropometrics and physical examinations, sample collection for novel tests. So this is blood, sputum, urine, etc. And they also underwent a WHO tuberculosis symptom screen and digital chest X-ray. And if positive on either, they underwent further investigation using GeneXpert and culture. And so the final endpoint classification resulted in 3 groups: prevalent tuberculosis, if they were diagnosed with TB at baseline or within 30 days of this baseline visit, or incident tuberculosis, or what we called remain healthy, and are actually moving towards saying no TB, because just because you don't have TB doesn't mean you're necessarily healthy. And so just to be able to apply this conceptual framework, I actually spent a lot of time defining reference standards Because how do you define infectiousness? How do you define presence of symptoms? How do you define chest X-ray um, pathology? And so the ICB framework actually provides a few suggestions of doing high fidelity reference standards, more operational reference standards, and then looking into the future. So we try to apply that same kind of thinking here, where we defined microscopic pathology per high fidelity as an expert radiologist review of our chest X-rays. So they would have had to classify them as TB. Infectiousness was defined by an endpoint review committee where we had to have four experts consensus that the person had either confirmed or likely tuberculosis. The other two options were possible or unlikely. And then symptomatology was defined as positive on the WHO for symptom screen. I will not present the operational reference standard today, but you can find it in the appendix of the manuscript. But the macroscopic pathology was defined as probability to be by a clinical officer that was local, infectiousness by positive expert ultra, and that is regardless of semi-quantitative readout, and symptomatology is any symptom. So it doesn't have to be the four symptom screen. And these are some of the other options that we considered here below. So before going into the multi-state model, some basic cohort description is important to give some context. So of the 2,100 participants, 21 people were diagnosed with prevalent TB and 43 were diagnosed with incident TB. And most of the people with incident TB were diagnosed within 6 or 12 months of the study. A notable mention is the nutritional categories, where we had 16% of people who were overweight or obese, and then 7% were underweight, and also 17% were mildly underweight. We had a 16% HIV positivity, and smoking was most prevalent in Zimbabwe, and as well as food insecurity and poverty. Though you can see that poverty, which is defined as being under 1.9 USD per household per day, was prevalent across all three countries. So then going into applying the ICE-TB framework. So just as a mention, I've included the cohort characteristics here on the right again. But when you try to split the group at baseline in the MTB non-infection, infection, asymptomatic non-infectious, and symptomatic non-infectious, this is what you find in the bar plot. So most of the people will either be in MTB non-infection or MTB infection here in yellow. And you can see that Zimbabwe and Tanzania has slightly higher prevalence of MTB infection, which is actually defined as Agra positive. I forgot to mention that in the cohort. And the reason why I did not include asymptomatic infectious and symptomatic infectious is because these people immediately exited the study. So to include them in the future multi-state model, they would have immediately been censored. So they're not included into this plot. So before modeling, we described the movement between states. So you can see here we have the start from MTB non-infection, MTB infection, asymptomatic and symptomatic non-infectious. And we applied these four categories over time, except they can see here in the top right corner that we actually have the two infectious groups. And the reason why they're just one up there on the right corner is because they're an absorbing state. So once you get to that state, you can't move to another one because they automatically exit the study and are initiated on treatment. So at each stage, they can move up to that top right corner. And you can see that most people in the non-infected group actually stay in the non-infected group. And the same can be said of those with an Agra positive, so who are MTB infected according to our definition. However, if you look down here into the asymptomatic and symptomatic non-infectious, it's quite a dynamic group. It's quite hard to see because it is a small proportion relative in the population, but about 30% go back to non-infection, some move back into MTB infection, and some progress as well to the asymptomatic infectious. But the main story is that at each visit, this non-infectious group, so as a reminder, it's defined as chest X-ray positivity or pathology, is highly dynamic, but a lot of them regress. So now that we've done this descriptive analysis, we thought, is there any way to actually model this? And this is where Michael and his expertise really came in. So what is a multi-state model, which is what was proposed to be done. And Michael, feel free to just jump in and interrupt me. I can't see you. So if you want to say anything, just interrupt. I don't know if you want to take the slide.
No, it's fine. Maybe you start and I'll add something.
Okay, perfect. So a multi-state model is essentially a generalization of a survival analysis to more than two states. So the way I describe it to people who don't do analysis is that it's just a lot of survival models in one. And so in your standard survival analysis, you have two states, alive to dead, or other states, but it's a single transition from one to the other. But in a multi-state model, individuals move through a standard and predefined set of states over time. So it can be alive, sick, dead, and you can add as many more as you want, well, depending. But the whole point is that you actually have more than two states, and each transition has its own hazard and timing or intensity.
Yeah. May I interrupt?
Yeah.
Okay. As you said, the standard survival analysis can be seen as we are a special case of multi-state models, only two states, and there are other very common cases. The competing risk model, for example, can also be seen as a multi-state model. You have got one state where you start, and then you've got two or three or more than this states where you can end. So that's the next step. And then there are models which are very common that are the so-called illness death models. You've got one state at the beginning, that's the person is healthy, let's say, one intermediate state, person is diseased, and then the final state person is dead. And you have three transitions from healthy to disease, from disease to death, but also from healthy to death. And this is a very common model. And then you can have much more complex models, as Leyla said. You can add more states to the model. You can add more transitions. For example, in the standard survival model, you've got only one transition from alive to dead. If you've got it's reversed, then I think it's not our department anymore. But in other models, you can also have reverse transitions. For example, in the illness death model, you can have from healthy to diseased, and you can also go back from diseased to healthy in some models, in others you can't. So this is a very wide class of models.
Amazing. Thank you, Michael. And so to continue, this really allows us to capture a bit more of a full disease history. And this is where it really came in critically into trying to move beyond this binary in tuberculosis to a spectrum, because the intermediate events actually matter. It's not event versus no event, alive versus dead, or no TB to TB. There is a spectrum of disease. And if we want to capture that intermediate, then the multi-state model proved to actually be a quite helpful application of this. So you can look at regression, progression, recovery, and relapse, and these can all be modeled jointly with many caveats, which we'll go into later. And some of the outputs are transition probabilities, state occupation, mean sojourn times, etc. Perfect. Do you have anything else you want to add, Michael, before I move to the next?
No, just to Nicholas' question on the chat, the short answer is yes, but we'll come to that later.
Yep. Yes. Okay. Sorry, I can't see the chat, so please feel free to shout out at any time. Great. So the building blocks of a multi-state model are the following. So we have states, similar to your more traditional survival model, and these are mutually exclusive categories that an individual can occupy. So you can have either transient states, so you can leave them. So someone can be in the MTB infected state and then move into a non-infectious state, or they can be absorbing, which is a state is a name that I mentioned earlier, and this is terminal, you can't leave it, such as infectious TB in this case, because they left the study. So they couldn't actually continue and occupy another state later down the line, or death, for instance. Transitions are directed arrows between states. They can be one way or reversible, and we'll show you the example that was applied to erase. You have transition intensities, and so instantaneous rates of moving from one state to another one, which is essentially a hazard function. And you also have the Markov assumption, So the future transitions depend only on the current state, but not the path taken. And then there are some different assumptions you can make here, which I think Michael will go into, but you can actually have semi-Markov extensions and assumptions where actually the time spent in the current state, so the sojourn time actually matters as well. And you can
Yeah.
also have, yeah, sorry, go ahead.
So no, didn't want to interrupt you. So go on.
Oh no, I was also just going to say the last point that it can be non-homogeneous. So intensities can also vary with time, so ca traditional calendar time.
Yeah, and I think the to add the number of states is always a point to discuss. I think usually one wants to have a lot of states because one wants to make it everything very detailed. But usually one has the problem that some states or some transitions are very rare, and then you can't really model them. So you have to combine several states and look at them together as we had also to do. Also for the transition intensities, now coming back to Nicholas' question, there's always the question how to model them. There are many possibilities. You can model them parametrically. You can model them via Cox models or something. You can add covariates, but you can also do it as a time constant and assuming an exponential distribution, which is of course in medicine not always the most realistic assumption or rarely the most realistic assumption. But I think it's a good basis to start with, especially if one has got the data to secure other assumptions. The Markov assumption is also a very interesting thing to discuss about because if it's really if the Markov assumption is really fulfilled, it's always not clear that often, and one can always discuss it here. The Markov assumption usually relies on the also has the or relies on a certain time scale. When you have the Markov assumption, usually look at the time from start of the study or from diagnosis and have a time scale that's going through all states, while the semi-Markov assumptions usually need another time scale, the so-called clock reset approach, that you start the time each time a patient enters a new state, which can also be discussed, of course, for our model here. We chose the clock forward approach, the clock starting at the beginning of the study, but as I said, this can be discussed. Yeah, that's what I wanted to say to this slide.
Brilliant. Thank you so much, Michael. So a few more details here. So these are mostly strengths and came back to the reasons why we chose to do this kind of modeling for our research question. So it handles competing risks naturally. And so there are multiple possible, essentially means that there are multiple possible next states from any state. There are reversible transitions. So like I mentioned, you can regress, which you could actually already see descriptively. So this allows for this to actually be modeled. It also accommodates for interval censored data. So as I mentioned, erase TB was only seen the participants were only seen every 6 months. So since we have these scheduled visits and we don't have the exact transition time, this actually allows for this. And we did use calendar time instead of visit one, visit two, visit three, but still the median time of the visit was still every 6 months. Maybe there was a month or two that changed, but you still miss quite a bit of time. And as you all know, as TB researchers, a lot can happen in 6 months. It also estimates clinically meaningful quantities. So as we discuss the transition probabilities over a specific time horizon, the state occupation probability. So that means it's the expected proportion at each state at time t. And that's the main result actually that came out of the paper, as we said, at month 12, how many people do we expect to actually progress to infectious disease, for example? And then the mean sojourn time. So how long on average is spent in each state. So Michael spoke a bit about the covariate effects. So the same risk factor can actually act differently on different transitions, and you can model this, though we did not, as we will go into the limitations. And it's also, it is a natural framework for simulation and prediction. So you can actually do this for other things other than just the spectrum. So you can look at health economics, intervention modeling, etc. And I will stop there for and leave it to Michael before I move on.
Thank you, Leila. I think it's a good point to talk about software. Here, we used R for modeling, which I think is, in my opinion, currently the best software to do it, or at least as I know. I think Stata can do it as well. Plus, maybe also able to do it. But in R, there are several packages: the MSM package, which you use, or the classic M-state package. There are also some others which are not that often used, but these are the main two. MSM has the advantage, or it was used here because it can deal with those panel data, which is, from my experience, very uncommon because I come from hemato oncology, and usually you know when people die or when people have a progression in leukemia. So that was very uncommon for me. It was what was very interesting here. And I think that's usually also the issue or the challenge when doing such a project. In the standard case, you usually have software, but then there's panel data, then there's, which later I think we'll come back later to, there are observations that are not completely independent. And then if you don't assume, for example, time dependent transition rates or something like this, it gets very difficult, and then you usually have to do it on your own. You can't use standard software anymore. You have to find your own solutions. Yeah.
Super. Thank you. Great. So already talked a bit about this, but the opportunities for application in TB is obviously disease and natural history, which is how we modeled it here. So we captured the dynamic non-binary nature of disease. And when I say we capture, we tried to capture. We're obviously limited by the data that we have, which is already quite well characterized when you consider the financial investment to doing these cohort studies. So you can quantify progression and regression, estimating the time spent, and which is a key input for transmission modeling. But you can also look on the post-diagnosis side. So we had diagnosis of infectious TB as the absorbing state, but it can also be the starting point. And you can actually look at treatment trajectories, so looking at cure, failure, relapse, and death, etc. It can also potentially be applied in the context of drug-resistant TB. So when resistance acquisition happens, and if there's any, and this is a bit more brainstorming. I'm not very well versed on drug-resistant TB, but there is also anywhere essentially where there is a trajectory and movement, I think you could apply multi-state modeling. And in terms of trial design and biomarkers, there's a lot they can add. And we spoke about this a bit before, which we didn't do in Erase TB, but adding covariates. So if you include, you can look at biomarker dynamics, and so change in CRP or host blood signatures, and you can equal these to state transitions, though you do need to actually mark and delinquent or like actually define the state. So I think that's a bit, unless you already know what you want to mark as a CRP, the host blood signature, as a certain measurement, it would be quite hard to look at these dynamics, but you could. And you could obviously look at health economics, looking at cost effectiveness, and new diagnostics. And I know there's a big move towards moving towards informing trial designs. So perhaps looking at informing sample sizes, how you define your endpoints and decisions. This could be a potential application of multi-state modeling. Perfect. So how do we do this in Erase TB? So we took our initial states that were proposed by the ICE-TB group. So you had your MTB non-infection. And I would like to quickly note that they actually proposed the word MTB elimination because the assumption was made for the ICE-TB that you actually at some point were MTB infection or part of this. So then you would actually go back to MTB elimination. However, this did not apply to Erase TB. You could very much enter the cohort having no IGRA positivity, no previous history of tuberculosis. So that's why we changed this wording. Yeah, MTB infection, and then you're asymptomatic, symptomatic, non-infectious, infectious. And these were the arrows we proposed. We said you can move between non-infection, infection, and back. You can do the same between infection and being asymptomatic, non-infectious. And then between asymptomatic, non-infectious, and symptomatic, non-infectious, you can go there and back. And then here you can see that for the absorbing state of infectious, you can't actually go back. So someone who's symptomatic, non-infectious may become asymptomatic, infectious, symptomatic, infectious, but the opposite is not true. You can't go back from infectious to non-infectious. And so what our main goal was to calculate the transition probabilities in a 12-month interval. So whilst we had 24 months of data, there was missingness. We had lots of follow-up in the study. It was also done during COVID. So we're starting to have more and more limitations of actually having missing data. But we had quite complete data at time 0, month 6, and month 12, which is why we set the cutoff point at 12 months. And Michael briefly mentioned this, but this is a study of household contacts. And so there is clustering. People in the same household obviously have a higher rate of being similar or higher likelihood of being similar to each other. So we wanted to include a random effect. But this was a bit difficult to do with the packages in R. So Michael very cleverly suggested that we actually randomly select one person per household and repeat the process 1,000 times. So all the results that we reported in this analysis are based on the average of the simulated runs. In practice, however, this is not what the model looked like. Unfortunately, even though we did cut it off to 12 months, our cohort was only 2,100 people, which makes modeling quite difficult. So what Michael suggested and mentioned earlier is that we actually group participants. So instead of having 6 states, we had 4 states, and we combined people that were asymptomatic and symptomatic non-infectious, and people that were asymptomatic and symptomatic infectious. So we resulted with a non-infection state, an infection state, a non-infectious disease state, and infectious disease state. And this was the absorbing state, and this was here the initial state. And we also added an arrow. We said, and this is also because of the panel data that Michael mentioned, that we see people every 6 months, that actually, even though you would biologically likely go through here, it would be we can't model this because this could happen in those 6 months. So we said that you could go from non-infection to non-infectious disease. And I now realize I probably should have chosen more different words because it's very confusing. And see, these are all the transition intensities that we modeled. So looking at our results, so this is what we're showing here is, again, the mean of the 1,000 samples that we run. And so we are looking at the probability of being in a certain state at a certain time. So state 1 is your MTB non-infection, state 2 is MTB infection, state 3 is non-infectious disease, and state 4 is infectious disease. So what this shows is that if your starting point is state 1, so MTB non-infection, at month 12, so here you've got about a 12.5% probability of being in state 2. So most people do stay in state 1. Same thing with state 2, that if you start in an MTB infection state, at month 12, you're highly likely of having stayed in that state. And from state 3, so the MTB non-infectious disease state, here we can see the dynamicity, which is already what we could kind of see in the descriptive analysis, but here you can see in the model as well that there's a lot more movement. So from state 3, if you start here, you are more likely to regress, so to go back to MTB non-infection and MTB infection. But obviously, a lot of the progression happens here. But I think the main point is that it's a very, it is a dynamic state. Not many people actually stay at MTB in non-infectious disease. You either progress or regress, which is quite interesting. There are, however, a lot of limitations in this study. There were very few that experienced disease states. So if you remember, only 43 had incident TB. We could obviously not use those with prevalent TB because they were immediately in an absorbing state from the start of the study. And due to the small number of people in the cohort, we weren't able to adjust for any covariates such as sex, age, and other things that we know are associated with tuberculosis. So I'll let Michael jump in here. I saw that you
Yeah,
muted you.
yeah, thank you. Yeah, thanks. I think what's also a limitation is here that I think the perfect way of dealing with the clustering in a family, I think it's clear that the samples are not independent within a family. It's an infectious disease, so I think that's very clear here. And I think the perfect solution would be to include some kind of rarity in the model or random effect or something like this. However, we didn't find any implementation in standard software. Um, and to do it on our own is not that easy. So I think here doing the simulation, doing it 1,000 times, or doing the sampling here, it was only the second best option because then of course getting the confidence interval, for example, which are not shown here in this very nice figure, but which are of course also important, are not that easy anymore, or something like this. Um, and I think that's a point open to debate, just if there might be a better problem. As Leyla said, there are very few transitions in the last states, and so the confidence intervals here are rather wide, of course. Yeah, and of course, what you also could discuss, I've talked a little bit about before, is the constant hazards over time, and I think that's, as I said, not the most realistic assumption. I think there should be some time dependency as usual in medicine, as we usually have it, but we were not able to model it here in a better way than this, and I think so. I think that's also justifiable. And yeah, especially as we don't have a true starting point, but like we usually have it in oncology, where time zero is the diagnosis of the cancer or something like this. So I think that's also the solution we chose here, but also that's I think up for discussion. So
Absolutely. Thank you. So to conclude, it was the first time applying the ICB framework longitudinally. And we did, as I mentioned, inclusion of other measurements such as CRP or host signatures could provide more granularity into actually defining the states. Your reference standard matters massively. And so, well, I didn't present this, but actually using the operational reference standard, the actual movement didn't change so much. It was more I guess, the proportion in each state that changed, but the dynamicity was still very much there. So that was an interesting finding. And again, there was an immense heterogeneity in the past following exposure to NTB. So whilst asymptomatic non-infectious was the most prevalent disease group, it was also very likely to regress, which like brings up points of, is the potential overtreatment if it's just based on chest X-ray alone, etc. We are writing this up currently in Erase TB, but because we followed people up quite diligently every 6 months, and if they had chest X-ray features, we actually followed them up a bit more intensively. We actually could see the regression happen because we didn't treat immediately if someone was trace positive, for example. So this is showing this in a model. We did find that multi-state modeling was a feasible way to predict transition probabilities over time, but there are some severe limitations that Michael mentioned. There's a few people that progress to an absorbing state, so our confidence intervals are incredibly, incredibly wide. So detailed observational studies are needed to better understand movement between states, and this is hopefully we can do maybe an IPD analysis, though it would have to have similar visit times, but maybe even platforms for trials, vaccine trials, for example, where you follow people up quite intensively could be a good opportunity to apply these kinds of models. And with that, I'd like to acknowledge the families affected by TB participated in this work, and particularly Rishi, Michael, Norbert, and Katerina, who were supervisors, and particularly Michael, who spent a lot of time not only helping out with this model, but also understanding TB, which is to be able to do this. So it's really, really appreciated. So thank you very much to our funders, and Michael and I are open to questions.
Fantastic. Thank you both so much. That's really, really interesting and a lot to get your head around, but really, really nice work. I think with a lot of sort of implications for those of us who, as you say, it was helpful to see that outline where you think it would be useful, because I think that's really very true. There are lots of different ways in which this influences how we do our modeling. Does anybody have any questions? Lee, go for it.
Hey, Leyla, thanks very much for the great presentation. I wanted to ask about your definition of infection. It seemed you were basing that on the IGRA test result. And I guess the concern that people might raise is that IGRA isn't always 100% sensitive and specific. I was wondering if you'd considered other possible modeling approaches, particularly with hidden Markov models, where you're kind of representing what might be a true underlying state, and you're then trying to model that kind of contingent on other observations, which might include things like the other biological measurements that you mentioned, CRP, IGRA, whatever other tests are being used. Yeah, it was just a thought. Thanks.
I mean, that's a very true and important limitation. We did try to do IGRAs of every visit, even though we know it's not a perfect test. What we are hoping to do is we're currently analyzing. So I'll answer the first part of the question. I think Michael can speak more about the modeling side and hidden Markov models, but we are doing additional information immunological analyses on the blood samples now. So hopefully going to get a bit more of an accurate view of MTB infection. But it was ultimately a trade-off that we had to make. We wanted something that was high fidelity for the modeling, but we also want something that can be applied. And most studies will use the IGRA, most studies will use TST. So it was a consideration. It's very imperfect. And even we also didn't have IGRA at every single visit. So we actually looked at imputing the IGRA results. So I will stop there and let Michael speak to the actual modeling side of it. But I completely agree, IGRA is not great.
I'm not sure if I got it correctly, the question about the hidden Markov model. I think hidden Markov models are models usually used for unclear or let's say misclassified states or something like this. And I think it's we had it shortly in mind, but I think as far as I understood, but maybe I'm not correct, we are rather clear according to this definition, we are rather clear about the states. We're not clear what happens in between, and we had of course to make additional assumptions how often patients go from one state to another, which is of course also an issue here. Was that your question, or did I get it wrong?
No, I think you've understood my question. It was really just just a thought, but yeah, thanks.
Thank you. Nick.
Yeah, thanks. And firstly, fantastic work. This was really great to see, and also really great to hear the sort of rationale behind some of the modeling decisions. Lee got to part of my point first. I also, think that, I guess thinking in terms of the definitions of the TB disease states, I always wonder if you did the exact same procedure the next day, to what extent, I say that as a heuristic for they should be in the same disease state. If you look at them very soon afterwards, would you see the same result? And so is there some kind of stochasticity in the test results, even from the expert line? And I think it's the same solution Lee mentioned in terms of a hidden Markov model, which would obviously make things more complicated. But I do wonder, how the results would change if you took that approach. The other one I wanted to ask about is if you focused on, if you were focusing on the sort of the TB infection part of it, you mentioned that IGRA positivity was seen as a one-to-one with being infected. I guess I've always wondered whether amongst those who might have truly cleared TB, there will still be an ongoing immune response. And so, I mean, the simple response to, solution to that would be just calling that state I don't know what it would be, immune exposed rather than necessarily infected. But it is a focus, a part of the field is understanding, do they have future risk? Thank you.
Yeah, two really good points. The first one, and that's why we use our endpoint review committee, because like I mentioned, if someone screens positive, even if they have a positive expert, then it takes about a couple weeks of investigations to actually determine whether we diagnose them with TB. So most of them that have been included here as being infectious, they will have undergone multiple experts over multiple days and weeks, cultures. We are quite sure that if they had TB on the day of diagnosis, they had TB afterwards, which is actually why we removed those. Anyone with only a positive expert was not included, because we repeated everything. So if they had a positive expert and then was not positive again, they were not in that infectious state, which it was a bit of an interesting approach to do. And I think we had a lot of discussions with other people that was a bit of sometimes rogue decision making that we wouldn't treat them immediately. But since we were following them up, we actually had that opportunity to do that. So the infectious state is actually the most clearly defined here. In terms of the IGRA positivity, I completely agree. I think we should have named the states IGRA positive and IGRA negative, to be honest. And I almost, in interpreting the results, you can almost lump them together, because just because someone is IGRA positive doesn't tell you anything in terms of, I mean, it tells you something, but in terms of actually interpreting these results, I find the most interesting is the non-infectious state. And if it regresses to IGRA positive or IGRA negative, I almost feel like you can lump those together, because of the panel data and it being every 6 months, you can be IGRA negative one day, maybe 2 days later, you're IGRA positive, and that's just not the day that we've captured. So that is a massive limitation of the data. So when I interpret it, I almost lump those two together, just because you can't really differentiate them due to the nature of what we have. But it's true.
Thank you. And somebody in Keppel Street in London.
Hi. Hi there. First of all, good luck in the final.
Thank you.
I think I want to echo also what Lee and Nick were saying about IGRA and infection. And I think you've answered as I would have expected, or like basically raising the fact that it's a perfect test and that maybe the infection was not the best name for the compartment that is basically being represented by empirical security. But just as an exploration, did you ever consider, I guess your model and the transitions are going to be determined by the baseline structure of the compartments, and it was like 37% that are going into this MTB infection compartment. Was there ever maybe a sensitivity analysis where you see what happens if you put, I don't know, say 5% or less, and how that influences the transition results?
Sorry, I'm not sure I understood correctly. So are you saying if we model a sensitivity analysis, assuming that not all those in the MTB infection group are in the group, we move them to MTB non-infected? Is that what you mentioned?
Yeah, well, I mean, the problem there becomes is where you move them. I think that's what we're mostly struggling with. But I can say that I don't think that there's ever going to be a compartment that is 37% MTB infection. So trying different ways of where to put them, sure, but I think that that state, it should be checked out to see what it does to your results if it's a much lower quantity or percentage of the population overall.
Yeah, no, that's true. That's definitely something we can consider. What we did make a decision to do, and I probably should have mentioned this, is actually if you look at the ICB framework, a requirement for being in the non-infectious state and the infectious state is actually to have a positive IGRA or not, is to be MTB infected, and everything else, we removed that requirement. So already those infectious and non-infectious states have removed the IGRA requirement from it. But I completely agree that would be very interesting. And I think it'd also be interesting to model them together, like I mentioned, and actually to remove the IGRA component and just have 3 states instead of 4, like we mentioned. But yes, that's definitely something we can consider. Absolutely. It's also cohort household contacts, so it might be possible that there might be a bit more IGRA positivity at baseline because we do recruit them immediately after someone was diagnosed with highly infectious TB.
I think it's also, I also thought about this question and Lee's question from the beginning, and I think that's a different hypothesis, isn't it? If you don't assume those are the states you want to examine, but these states stand for other states that we don't really can capture. I think that's where indeed a hidden Markov model would be an appropriate question. But as far as I understood, that's not the question we wanted to answer.
Agreed. We saw it more of a limitation for the main question. Yeah.
Thank you. And I think there's another question from in the room in London.
Thank you. Great. First thing to say, yeah, Leyla and Michael, I mean, a beautiful analysis and a really beautiful data set. And I've got they're two kind of meta questions, not about specifics of the study, because I think it's a beautiful study. There's many things that we will have a strong interest in. We will have, we can interpret this data in different ways. One is around how open would you, and how much time do you have, and how open would you be to tweaking some of these assumptions? Like, for example, I mean, just because it's been mentioned, the assumption that Albo's just made. So, I mean, I think this is a beautiful data set, it's a beautiful analysis. I think it can be really important for the field. Would you be open to, for example, just taking some questions from folks, and if we could suggest some hopefully reasonably light tweaks to what you've done, to sharing the results informally, formally, however you'd like to do it. Because I think there's real goals here, but there is genuine uncertainty about, the way the world works and for example, where those IGRA folks should go. Which would really, I think, be a benefit to the TB community and make the most of this data set. So it's more, it's how open you are to kind of tweaking this a little bit to see what else it might say.
Absolutely. I mean, I think I love this analysis, and the reason why I love this analysis is because Michael came in and had this brilliant idea. And I think with TB, you need to crowdsource ideas and tweaks. And I think I have the time, I'd be happy to collaborate with someone to do this analysis. I completely agree, Richard, that erased TB is a great study. Bias, obviously, but I think there's a lot of things that we can do with it, and it would be such a shame that we spent years collecting this quite well-described data every 6 months, and the work continues beyond the PhD. I would be delighted to do additional work, and any input and any suggestions on tweaks to this model, but also other models, other things we could consider and how to look at this data would be fantastic. And in the next few years, because we're now analyzing the blood samples for signatures and everything else, we can start thinking more about how to incorporate that kind of data, maybe how we can link to other cohorts as well. So absolutely, yes.
Yes, and that and Michael, is it the same for you? Is that roughly the same place? Michael?
Sorry?
I was asking the same question to Michael, because obviously he does the modeling.
Okay, sorry, I had some problems. I don't know if it's your mic or my earphone. So, but yeah, from my point of view, sharing the code isn't a problem. I think what the data, it's not my data, so I can't have any decision on this. And I think that's
about Michael. It's more about personally, I wouldn't have time to take your model and rerun it. But what I think would be quite valuable is if, for example, Malbrew sent you an example saying, rather than starting everybody assuming everybody is IGRA positive and infected, let's say, run the same scenario, but assume that half of those folks are infected and half of those folks are not. So it's just a small tweaked model.
Okay.
And see whether it makes a difference or not, or what difference it makes.
So, sounds interesting, yeah.
Yeah, fun. Okay, good. And then the second one was actually on a very specific question. So I've already, Leyla, I've already chatted with Claire about this. So my really strong interest is trying to understand the progression rate from asymptomatic TB to symptomatic TB, because it actually has a $100 million advantage for vaccine trials. I know we talked a little bit about looking at the data in that way again, but we haven't got there yet. So it's whether you think you're still open to that, and maybe we can do a little bit of work there.
Yeah, absolutely. We can maybe take offline and see exactly what you need and what you'd like visualized or shown, and we can work on that.
Brilliant. Thank you. That's all from me.
Thank you very much. Any other questions from anyone?
I think I'm curious about, so you've got serial chest x-rays. Have you looked at all at breaking them down? So people who've got signs of TB, whether they're getting worse or getting better. So with that, maybe a better indication of, I don't know exactly where I'm going, but something to be interesting to look at.
It is, and we are looking at it. The chest x-rays are fascinating. Also because the clinical officer read them. We have CAD4TB version 6 and 8. And we had this expert pulmonologist review them, which was what we use in this analysis. First of all, the rate of discordance is quite interesting. But the trajectories, again, are very interesting as well. There's some people who the expert pulmonologist called us and said, have you treated this person? Because they have full-blown TB and they never had symptoms, never had anything. The clinical officer didn't pick them up, and then they regressed. So some people have quite interesting patterns. Someone is now currently looking at describing this descriptively and also maybe doing a bit of a clinical report, looking at the chest x-rays over time. And we're also going to do some modeling to look as well. So this is ongoing analysis, and hopefully we'll present this in the next few months or look for feedback. Unfortunately, it won't make it in time for the union, but it's ongoing. Absolutely.
Yeah, look forward to those results. And just a quick follow-up to Richard's comments about symptoms. I mean, as I'm a massive skeptic about symptoms, right? It all comes down to who your interviewer is, whether you report symptoms or not. So I think in doing that analysis, I would also incorporate the data on changes in symptoms for people who perhaps don't have TB at all, right? Because you might find that, one survey, one context, one lots of interviewers, only 5% of them report symptoms, and the next is 30%. It's carrying forward. That change also will apply for people with TB rates.
Yep.
So it may not affect developing symptoms very much, but this particular survey multiple important symptoms. So somehow incorporating. Yeah, I think that data tends to get thrown away, right? Making sure you incorporate that into the analysis.
Yes, absolutely. Definitely. Thank you.
Thank you, Nikki. Any last questions? We probably have time for one last question. If not, then maybe I can ask, as somebody who's not hugely familiar with this, it looks a lot like work that Catherine Horton, who I think might be on the call, did before, basically taking a modeling approach and looking at that. And this just looks like the sort of the empirical version of that. And I didn't know if you had compared your results to that, and if it is comparable, and if so, if there are differences in where they are and what they tell us.
You mean the results from the publications of the spectrum? They are very similar. Yeah. So if I remember, and Catherine, correct me if I'm wrong, but it was also lots of regression, and there was some progression, but it wasn't as much as one would expect. Because I remember it's obviously in the discussion of the paper, but it's been a while since I've thought about this analysis. But it was very similar. Nothing unexpected.
Thank you. Oh, I'm getting a thumbs up from Catherine as well. Thanks, that's really helpful. Brilliant. And we're probably out of time then. But thank you, Michael and Leyla. Thank you so much. I think, as everybody has said, really, really interesting, fascinating work with lots of implications for everything we do. Thank you so much, and hope you rest of your day.
Thank you so much.
Thank you. Thanks for the invitation. Bye.
Bye for now.
Bye bye.